Good morning, everyone. Welcome to a presentation on practical comminution process improvement opportunities. This is something I've specialized in for some time, coming out from my research into the applied side, applying the research, and been doing more and more of it recently. And I'm going to today do a bit of a flyby on a collection of case studies rather than a carefully structured introduction. It's much more, I think, engaging for you to see a couple of interesting examples of what I mean by improvement opportunities that are staring at us in many of our plants. So if I think more holistically about a plant, we tend to, when I go to site, I see people thinking about a specific part of a problem. But one needs to appreciate you've got a unit within a complex system, and these systems are highly interactive. The different parts of them are coupled and interdependent. So really one of the big things to bring into the awareness when you're addressing a problem on site with an issue is look beyond where everyone's staring. Look around upstream and downstream to see where the cause and effect is. So as an example, and these are, as I said earlier, they're all real examples. And I'm at a ball mill, they've got a low throughput, a coarse product, and everyone's saying, well, we need larger balls, we should speed up the mill, should put a ball retaining ring so we can load it up more, and they're asking me for advice. But if I look a little bit upstream, and someone else is asking for independent advice on the device upstream, which in this case is an HPGR, they're suffering from low specific energy numbers. The gap's higher than they would like. They've got a coarse product, and so they try increasing the pressure, and this HPGR begins to vibrate. So blame the supplier. It's the wrong equipment, or there's something wrong with it. And you coarsen the screen aperture because it overcomes the problem. So I wonder if that's the real cause of the ball problems. As I look upstream from the HPGR, walk up the circuit, and there's a secondary crusher preparing material. And I notice there's a rather coarse chamber design and a pretty wide close-side setting, and they're struggling with capacity. So they kind of accepting low utilization as a reality, or only operates at about 60 or 50% of power utilization, something wrong with the design. Then I look upstream again, I go to the primary crusher, and I see a really wide open side setting, a close side setting. So what's the issue? Well, the guy says the rocks are large. So I've had to open up the closed side setting to increase the life of the liner and just to get the trucks through the queue. And the real cause is a coarse blast. So the reason at the end here for this ball mill overloading is a coarse blast, and it knocks into every piece of equipment down the chain. And then you see it here. And trying to solve this problem, you're just dealing with the symptoms. That's the cause. And that's what I mean by a coupled system. And this type of scenario is quite common for me when I'm dealing with issues on site. And then when you look at a circuit, this is actually a big porphyry copper one, but we've got two 20 megawatt mills running, one running at 15, one at 16, ball mills below installed power, two different P80s, 230 and 190, different recoveries. So now I look at this, I see you've got 13 megawatts not used. You have a spare ball mill in the circuit you're not using. And if I compare that circuit, 83% recovery, to that 87, there's a delta of 10% capacity and 4% recovery. So if we can get them both to match line 2, you've got a huge improvement on your side. But again, in this instance, they're looking at, well, should I put coarser balls in, and should I change something here and there? They're not focusing. The real issue is you're just not drawing the power. So look at the circuit and what's the high level issue before you get stuck into some detail. So what I'm hoping with a few examples to give you insights into the drivers of effective comminution operation and how do you identify them. And the pictures have me inside mills, and I really emphasize you've got to be there and look at it. Looking at process data from a distance just doesn't give the inside story. And so actually feeling it, measuring it, listening to it, this is how you get the insights. So another example of the coupled system. I'm going to have a few examples here. I've numbered them just to keep track. Here is the problem with a cyclone and coarse feed. So you've got this coarse product feed into this flotation, coarse product from cyclone, and it's on the coarse side of the ground recovery curve. Quite often it's there, and they're playing with the cyclone. But when I look at it, there's this complete changes. Sometimes really coarse rock coming in, and sometimes, as they call it, garden dirt. And so when you've got this coarse rock, the system overloads, and there's too much recycled rock, and the belts, conveyor belts overload and spill. And the sag mill down here, the power is all over the show, because this is not varying once a week. It's varying every few hours or every hour, randomly, depending on what truckload arrived and went through the stockpile. So this is all over the show, the sag mill, which passes on to the ball mill, which passes on to the cyclones and recovery. So while they're trying to fiddle around here, the issue is the ground, the blast. So the unevenness of the blast. So they're not blending and maintaining consistent feed to the mill. That's the source. That's where they need to look. Another really common one, example 2, I call it insidious segregation. When material comes off a belt, the coarse stuff always goes further than the fine. It's just physics. Really nice illustration here. You can see the coarse rocks, the fine on this side, a dump truck area with the big rocks down the side. The impact of that can be quite significant on operation of a plant. I come from a comminution milling background, and slowly I've evolved to paying more and more attention to materials handling. So when we look at this, what's the influence on your circuit? One of them, this is uneven feed into a bin, that conveyor going into a bin. It's preferentially throwing the coarse rock on one side and fine on the other, and building up a slope inside the bin. So it's not filling it evenly, it's pushing it to one side. So losing about 50% of bin life capacity through that, and then trying to pull one side feeder harder than the other to rebalance it. And the consequence is one overloaded screen. There are 2 screens at the bottom. One overloaded, the other underloaded. We did the surveys. We measured the capacity. We modeled the capacity of both were evenly fed, and it indicated 20% more capacity. And that was achieved by changing the feed. So we put a deflector at the top and made sure it fell centrally into the bin, better mixed, 20% more capacity. And that was a limit on the entire circuit. So we took away a bottleneck and opened up the capacity in the circuit. Another common area for segregation is at transfer points is into a crusher. So here's a feed going into a crusher, and look, it's fine on that end and coarse on this side. So there's clearly a segregation going onto that belt. Here's another one where it's coming off the belt into the crusher. This is a crusher chamber, coarse on one side, fine on the other. Normally you would have a feeder between this. This is quite a small plant, but you might have seen ones like this as well. When I look from the top, we can see coarse on one side, fine on the other, or fine where it comes in and coarse at the other end. When I stop the crusher, I can see where the coarse and fine is. Does it really matter if your crusher is a bit segregated? Oh yes, it does. So we use discrete element modeling. We can solve these really well by putting deflectors and mixers and slightly changed angles and things like that. The way we diagnose this, I do with Magnus Evertson from Chalmers University, who's my crushing expert. I do all my crushing with him. Is we sample either the power or the pressure. So if you've got a hydrostatic crusher that's hydraulically supported, you can then measure the pressure, which is the best. Otherwise, you measure the current at the motor and you sample at least 200 hertz. So you don't see this in a control room. Control room, the best you see is 1 hertz. So all of that would become one average signal. This is 1 second, 200 hertz, 5 oscillations per second of the crusher. So they're 5 peaks. And if we convert it into rotation of this mill, so we can actually track time around the crusher. So if we could convert the time readings into spatial, shall we say, we can see this end, there's low pressure, at the other end high here, low there, and that relates to the spikiness, but it's in a position around the crusher. Ideal would be even pressure around the crusher as it oscillates, but the polar coordinates show it's clearly not. And the pressure range is 4 megapascals, 5 times a second. What does that do? You get preferential wear spots, burnt out bushes, nuts start getting overstressed and cracking, and eventually the main shaft breaks, which should last 20 or 30 years. So there's big mechanical playback on you for that. And the mechanical people aren't happy. They open the closed site setting and say the crusher can't take the load. It's not the crusher can't take the load, it's that the load is so spiky. So you have to drop the entire feed rate and open the closed site setting to get rid of these spikes. So these spikes here, you're trying to get rid of those. And then you're sacrificing your crusher, you get half the potential. If I feed it evenly, I can get up to the crushing potential. So it's quite a straightforward one. We did one recently. They were getting three weeks of crusher life in the chamber. After we changed the distribution coming in, after 3 months, they still had the same chamber. So that's a significant change in life. And they were getting a finer closed site setting and a higher throughput, like everything you want on. So that's a really good opportunity around desegregating segregated feed. So I've given you some stuff on segregation, which affects especially crushers and screens. Whether it's segregated into a mill doesn't really matter, so we won't worry about that. But in mills, it's a subunit that's highly complex. So you have sag mill is affected by the feed size coming in, and the feed size also forms the grinding media. And the grinding media affects the energy distribution, and the energy distribution affects the grinding rate. These things are highly coupled. So if anyone did a off-the-page engineering design, you shouldn't design something like this. It's too coupled, too interactive. And then on top of it, there's a discharge system with variable efficiency or inefficiency in the discharge, affecting transport through the mill. So all of these are coupled. Then operators have different theories about stuff, and you do different things, and it looks like you can solve a problem with different approaches. It's because the system is so complex. So in that complexity is these dynamics of the process. This is not a stable system. The mill is intrinsically unstable. The feed is not stable. The contents are changing in a sag mill. So what we should do at the very least is make sure our control system is stabilizing, not amplifying. And it sounds like a silly statement also, almost like, of course, the control system is going to stabilize. Not necessarily. When I see a lot of reactivity in a mill, control, load, feed rate, speed, I'm immediately suspicious of the control system. And my method is to turn it off, which people find difficult to handle, but I ask them to turn off the control system. It's totally manual. I set it to about what it was doing for the last 4 hours, speed, throughput, water addition, and then we let it run. So an example, 40-foot mill, running at around 3,000 tons an hour, so a huge throughput. I just switched off the control, 2 parallel mills, switched off one of them. Over 3 hours, we raised the power by 2 megawatts and the feed rate by 10%. So just slowly crept up the feed rate. Little 5-ton per hour increments over this period, kept it quite stable. And then because I'd stabilized it, despite having a higher feed rate, and I had more power, but despite a higher feed rate, we've got a finer grind, a more stable grind going to the ball mill. And the recovery, it was enough time to measure the online recovery downstream, had gone up. So complete win, and I'd switched off the control system. So nothing special on my side, just stabilized it. So it showed bad control system. The plant manager officially threw it out the next day and they got a new control system. The other thing is sump control. Independently, it wasn't this example. I just switch off the sump control, which is trying to hold sump at a certain level. Sumps are not there to be held at a level. They're a buffer. If you hold them at a level, they become an amplifier of disturbance. And I've switched off a sump that was in 5-minute cycles, increasing and decreasing the pump speed and the water, and everything's going crazy. Just turned it all off. Fixed water, fixed pump speed for 6 hours. We didn't touch it. So I just set it at the average, watched it, tweaked it till it was within the range, and we just walked away. Of course, because the control was off, the operator had to keep an eye that it wasn't gradually filling or emptying as milling conditions changed or feed type. But in principle, it showed how ridiculously over-controlled sump was. So I'd really watch for those, because that's just straightforward, simple opportunity. This I've published multiple times in grind curves. I'm not going to go into it today, but the principle of I've slowly changed the feed rate, that's this brown line, in these tiny little increments, like a ton or 2 tons per hour per minute. Little step, wait, little step, and then pause and watch what the mill does. And there's this big lag. I start increasing the feed rate. It takes 35 minutes, then 30 as the mill is filling up. So that's that big lag I want to emphasize today, is between an input and a reaction of this huge mass of rock inside the mill. So the temptation with operators is to over-control and control systems to get a quick response. All you're doing is having a quick disturbance, introducing a huge disturbance into the system. So over-control, I observe, is a common problem that's quite easily addressed with a improvement in the control system. So this control, the person sitting here has a significant impact on profitability of a process and the control system that's behind it. We see really different styles of control system, multiple screens, videos and things, and it's quite complex for an operator. But some standard rules or guidelines should be followed. Look at this one on the right. These are 2 sag mills in parallel. And here's one, and you can just see all over the show, the power's all over the show. And this one's pretty stable. And this is stockpile dosing. They were short of feed because of primary crusher problem. So they dosed in the stockpile to keep the feed rate going. It didn't solve it. It just meant the stockpile was empty, and then they had to switch off a mill a while later because it didn't create more rock. That's what I try to point out. Dosing the stockpile doesn't create more rock. So you just have to fill the stockpile. You're not filling it, so you keep dosing. You're not filling, keep dosing, so you get locked into the cycle. That's stockpile dosing. And there's the parallel mill, absolutely stable. Here's another example of really bad fluctuations. Now think what that's doing for recovery. So the product size is all over the shop going into the flotation. So your recovery is going down. And instead, just wind back both mills, run relaxed, run it stable at a slightly lower throughput, keep the stockpile stable. And when there's more feed, well, the stockpile will fill up again. So it's this impression that we'll keep feeding regardless, and then we'll blame the people upstream. It's their fault they didn't send feed. That doesn't help our cause, I'm afraid. So stability. So here's another example of over control. On the left, this is a 24-hour period, different side altogether. It's quite a small feed rate. It's a little mill. It's a little gold mill, you know, somewhere between 150 and 350 tons an hour, believe it or not. Cycling during the day, that's a huge variation in feed rate that we're seeing. And look at the power, up and down and up and down, you know, 300 kilowatts, 350 kilowatts, the bearing pressure all over the show. What we're seeing here is it's running along and the operator thinks it's low enough, so they start ramping up the feed rate to get the power up. But the power lags. So it was actually busy in a grind out, in a grind out. So it just carried on grinding out for a bit. It was losing mass. So the operator panics, feeds more and more and more. And it's coming in the front end, and the fine stuff is pumping out the discharge end. And then it turns. So he drops a little bit, oh, it's not there, and he pushes it up. And now the power is going up extremely fast. So he realizes there's a problem. brings it down. And this cycle just carries on through the day. If we go into specific energy, kilowatt hours per ton for the same period, and I say, what's the specific energy? It's varying from 7 to 12. What's that doing to grind size? The grind size is all over the show. There's absolutely no reason to be doing this. I could bet my bottom dollar I could just lock this at 260 or so and just leave it, and it would stabilize. This is not feed variation. This is operator induced. It's really clear when you get these cycles like this and these big changes. This is not variability in feed. This is operation. So look for cyclic interaction. These are cycles, they operator induced. Another variation we have in milling that's cyclic is between liner changes. Here's a major reline, a small reline, a major reline. And look what happens. During a reline, the bearing pressure should go down because the line is getting lighter, but the power's going up. So it goes up by 500 kilowatts or 450 kilowatts on 3,000, so 15% over the life. And they say, well, that's it, the liner has to run in and things. Then we backfitted the JKMRC MillFit software and calculated the filling. And sure enough, the real problem was that the filling was low to start with. So low power, no surprises. And it slowly filled up over the life of the liner. Why? Because they were running at a fixed bearing pressure. So as the liner lost mass, there was more and more rock in the mill. Till at the very end of the liner life, they had the right amount of rock in the mill, the right filling. So that's another one to watch out, especially as a liner supplier, that they're actually keeping us, they actually know what their filling is and are controlling to that. So we see with a new liner, low filling, and a worn liner, high filling. This is really undesirable because the new liner is the most aggressive. So you get liner damage, so they slow down the mill and you lose even more power. So this is a common problem. It's not unusual. So jumping forward to slurry pooling, being well recognized for at least 20 years, but still I'm finding it quite a lot around circuits. If you look at the end of the mill, you can see, if you can get a view in there and you use a fan and a strong light, you can view the pulp coming down. The mill's rotating clockwise here. The slurry gets carried all the way around and only flows out on the downward side, on the back of the pulp lifter. You've got slurry constraint issues. It's absolutely clear. It should be flowing out this side. And if you want to take it on a mill, here we've switched off the feed and you immediately see the load going down and the power shooting up over a few minutes. Only one thing can do that is slurry discharge. Nothing else can switch it like that. So you can actually diagnose on the fly, stop the feed for 2 minutes. This is, that's actually in a ball mill, but the same effect where the power and the load mirror each other. So as the load goes down, the power goes up. Load goes up, power goes down. It shows the mill is overloaded. And here's an example. I'm running a mill and suddenly the power just drops. A slight change in ore type, a bit more viscous. This mill was on the edge of slurry pooling all the time, and it just lost it. Lost 1.5 megawatts, 1 meter deep slurry pool. Pretty impressive. So these things you can pick up on the fly that they're happening, and then you have an issue to address. If it's happening once a month, that's okay. If it's happening every day, that's not okay. So we've got through slurry pooling and now mill filling. And you think, well, people should know their mill filling, and as I showed in the example of that mill over life of liner, they had no idea. And here's one, they've crash stopped, it's right where they expect it to be. With Aubrey Mainzer, this was a surprise to the operation. We diagnosed it was overfull the mill, and sure enough it was. This was one that when they originally stopped, it was to the top of the trunnion. We couldn't pull the trunnion. This is after grind out. So this thing was 60% full. Here's a mill in the process of overloading. That's the next day, 1.6 meters above here. If I take time here, mill power is going up, bearing pressure going up, operator, the control system factor is just pushing, the power starts going down. And there's no logic in their control that says, hang on, that's a problem. So it just keeps increasing the feed rate. And the bearing pressure goes up, pushes the feed rate, bearing pressure goes up. But the power is going down, so it gives it more feed. Until the mill tripped. And it had an extra 120 tons of rock. So it's 90 tons above a 35% filling. This thing was at 59% filling. So these can happen. So this was a lack of understanding of the operator, but also the control system should easily pick this up. Plus, it turned out the safety limit on the bearing pressure was completely wrong. So there are a number of factors came together to lead to this. But it's, I've heard over the years more examples than people would admit of mills going into total overload. And I've just shown you 3 photographs that I've been in, but not caused, let me tell you. I didn't cause that overload. So again, looking at the estimation of filling, they thought they were running 35 to 40%. Their bearing pressure, they're kind of, this is what we do when we stop and it looks okay. I used just power and said, oh, this is more like 35 to 20% filling these 2 periods. I could calculate just on that, but I said it doesn't add up. We need to have a proper look. And Mosen and Marco from the JKMRC went up to site and they installed the MillFit software, and they had to calibrate. They checked crash stops of the mill, grind outs, the ball level. They found there was an issue with the slip energy recovery in the motor, giving the incorrect power reading. They discovered that the bearing pressure hadn't been calibrated to calibrate by temperature and pressure. And there's also a load cell that was off center, giving an incorrect reading. 3 things were wrong. They had to calibrate all of those to solve the problem. When they back calculated, it was actually running down here, 26% early stages and then 18% filling later stages in this period. And the ball filling was 16. There's almost no rock in the mill. And they destroyed their liners. No surprises there. So this is something that's quite common, not a good handle on. So if you're going to check your ball load, grind it out properly till they're just balls. Not, well, it looks like 10% rock. No, it's got to be clean for you to know it's ground out. Measure properly. Marco's published a paper here, Hilden and myself, measuring from outside the mill, really accurate with a laser, so that it's done properly, not guesstimated or estimated about this many liners. Get a good handle on it. It's such an important factor. Just skipping on to ball mills. Ball mills also overload, but quite differently to sag mills. I crash stop a mill, which is highly unpopular, but I've done dozens and dozens of them. You just got to make sure the cyclone doesn't get drained back into the pump and the pump gets choked. So you should open the pump if that's a risk. And you look inside and look at these rocks. These are in the discharge. That's in the discharge of the mill. There's this thick slurry and pebbles in the mill. It should be clean. There should be water on top, that's okay, but it should be clean with the surface of the balls. This is overloaded with rock and it pushes down the power. So we see this mill, way below, there's the power should be running here near 1350. They're down here. I'm wondering why. When I look at the power curve, bearing pressure, proxy for mass, no, bearing pressure is not weight, it's a proxy, and power, as we load up the mill, the power is going down. It shows the mill is overloaded, not with balls, but with rocks. It's overloaded with these rocks, and that's causing the power to drop. I'm just dealing with a few sites with that same problem. So if you see the signature and poor utilization, look upstream, that there's coarse material coming into there. Another signature, suddenly the ball mill power goes down, circulating load up, it's overloaded with rock. And the cause is the screen. Poor wash water, coarse screen, this one's really coarse. These pebbles are getting through into the ball mill. Another ball mill with rocks in the discharge. It also disturbs the cyclone. So the cause is, it's too coarse, the screen on the sag mill. So fixing the screen, which I published on, really good sprayers, good quality screen, that actually solves the problem. A screen with good wash water will set up at least 20% more capacity, and then you can make the aperture smaller again. So on one side is not these two. We moved the screen from 15mm down to 7 by them fixing up the screens, and the normal overloading went away. So I've also published on this endemic issue of mill overload. 8th area, classification not ideal. So, ideal classification would be a straight line. Coarse goes back to the mill, fine goes off to your recovery, but the reality is it's slope, and oversize goes into the next stage, into your recovery stage where it shouldn't, and the fine goes back to the mill. Overgrinding and lose capacity. So this fine stuff robs capacity. It doesn't go through for free. It does. The mill does work on it and it gets finer. In the coarse stuff, you lose recovery. So this is kind of the extremes of the losses you can have. So that forgotten cyclone at the top of the cluster, pay attention to it. Properly set up, proper control. These make a huge difference to overall profit. I see cyclones next to each other, one roping, one okay. 4 cyclones in a cluster, completely different cut sizes in each of them. Single cyclone in 3 seconds, flaring and collapsing, so inadequate pressure and cycling in the pump. All of these are just metallurgy 101, and it's quite common to see these problems. So I'd be looking there, something like the Multotec Celis, to look at the flare angle, really keeping an eye on the cyclones instead of them being hidden. This is such an easy, cheap way of getting more out your circuit and more recovery. And it leads to issues like not understanding the effect of feed density on the P80. This is changing pressure, and it's like this box diagram. It's all over the show, the P80. But if I look at feed density, it's really sensitive to it. So it should be the top tier of control is to control on density or control the cut size. And when you get your density too high, the cut size goes crazy. So you've got to stay in this range. So I see a lot where they control you on pressure. Why? Because it's incorrectly set up pressure-wise. You get these big steps as you turn cyclones on and off. Sort that out, that you've got a range of pressure, and then you control on density. It is the top tier of control is density. And this is an example of very good work by Aubrey Mainzer. Closed loop test, but 3 spigots. So it's a full D20 cyclone. And we can see in this fine cut size, 17 micron difference on around 45, 30% difference in size from the 82 to the 102, which you can compensate as it wears with density. So you can play these two together to control your cut size. So this awareness that if you're letting spigots wear out differentially or not compensating, the big effect it has on cut size. So I've published as well in the Seek the Future areas of looking at energy, understanding energy, which I won't go into today, but another way of looking size-specific energy, overall equipment effectiveness, practical knowledge, you put them together to understand where these opportunities might lie in a circuit. So I'm going to jump over SSE, linear relationship between energy put in and grind size. So you can read my papers on that to get more about that. Incredibly useful and simple tool. You just need one size, one sizing to get this. And I can differentiate between equipment. And OEE that Magnus brought me attention to, you look at basic cumulative distribution and where are you below where you'd like to be. It's a nice way graphically of illustrating, and it gives you a single number. My OEE is 72% and it should be 96. That's not too good. OEE is 96 and I'm expecting 96. That's cool. Look somewhere else. So these help you, guide you to where the issues are on site. So closing off, where are the opportunities? How would you address this? I've just given you, this flyby of the potential areas you can look at around the circuit. So I hope that's been really useful to you. Quite a lot to absorb, but hopefully engaging and fun to listen to. Thank you.